Hello everyone, this is Jiangpeng He from Purdue University School of Electrical and Computer Engineering. So the title of our work is Online Continual Learning via Candidates Voting. So continual learning aims at learning new tasks without forgetting the already learned knowledge. And in this work, we study the image classification problem. So the new task here refers to the new classes as shown in this figure. So each here refers to the model in different steps, and during each continual learning step, only the new class data is available to update our model. And after each step, the updated model should perform the classification task on all the classes seen so far. However, most existing work addresses this problem in offline scenario, which assumes all new class data is available at once before each incremental step. In this work, we focus on a more challenging online scenario that the data for new class becomes available sequentially before each incremental step, as shown in here. So we update our model step by step and use each data only once for the training. Here is the motivation of this work. Firstly, the parameter bias in the classifier is one of the main reasons for the catastrophic forgetting as analyzed in existing work. As shown in this figure, the prediction is always associated with the largest output logics. So the parameter bias in the classifier will lead to the biased prediction towards new classes that will result in the forgetting problem. However, the existing work also shows that the classifier can still maintain the discriminativeness for each learned task to make correct predictions. So as shown in the lower half, instead of using the highest output logics as the prediction, we first select candidates from each learned task and then generate the weights for each selected candidates and combine them together to make the final prediction, which efficiently addresses the forgetting problem. So the question here is how to obtain the largest output logic for each task and how to generate the weight for the final prediction. In this work, we address both questions by using the exemplar side. First of all, in the learning phase, we propose an online sampler which is capable of selecting exemplars from data string based on the class mean. As shown in the equation here, we update the mean vector by using each new observation, which does not require knowing the total number of data beforehand. In addition, we store both the class index and the task index along with the selected exemplar. So during the inference phase, the task index will be used to generate the binary mask to obtain the highest output logic as the candidates. And also we apply a pre-trained feature structure at the beginning to store the feature instead of original images as the exemplars in the exemplar site. So during the inference, we calculate the probability for which learned task the test data belongs to as the weights for each selected candidate to make the final prediction. And finally, we also investigate the feature space data augmentation for the stored exemplars to further retain the learned knowledge. So specifically, there are three main steps in inference phase. Firstly, we extract the maximum value of each learned task by multiplying the output logic L with each binary mask that generated by using the exemplar set. And we use the normalized value as the candidates. And then we design a probabilistic neural network, PNN here, to calculate the distance between the feature of test sample with each stored exemplar in the exemplar set and use the output probability as the weights. And finally, we combine the extracted candidates and the generated weights to make the final prediction using the equation shown here. So the gamma here refers to how much we can trust the obtained weights, and a higher value refers to the higher confidence. Here are experimental results. We first compare our method with existing online continual learning work on 3 benchmark datasets with a fixed memory size with Q equals 2000. As shown in these figures, our method achieves the best results with the highest accuracy for each incremental step. For future work, we will focus on the unsupervised continual learning, since most data are obtained without label in real life and the label annotation requires plenty of time and human resource. So one of the possible solutions is to use the pseudo-label instead of the human annotations. Thanks for watching, and please send us email for any question.